This video is about matplotlib.pyplot. PyPlot is a convenient and easy way to access the functions in the powerful Matplotlib visualization and plotting library. There are links to the official tutorial, the gallery of things you can do with Matplotlib, and the list of functions in matplotlib.pyplot at the top of this notebook. To make matplotlib.pyplot work in a Jupyter notebook, so that the plots appear actually as part of the notebook, you need to include the magic command at the top of the first code cell there. That's the line beginning with a %. If you change the word inline to something like notebook, you'll get different looking plots. On the third line, I'm going to import matplotlib.pyplot as Plt so that I can use functions from matplotlib.pyplot by calling Plt and then a dot and then the function name. Now that that's imported, let's move on to the simplest function in matplotlib.pyplot, which is Plt.plot. You call Plt.plot by giving it a list of x coordinates and then a list of y coordinates, or alternatively a NumPy one-dimensional array of x coordinates and y coordinates. What Plt.plot does is then draw straight lines from the first pair of coordinates to the second pair of coordinates, and then from the second to the third, and so on. In the next code cell, I've called it with a list of x coordinates 1, 2, 3 and a list of y coordinates 2, 1, 2. That means this Plt.plot command will draw a line from the point at coordinates 1, 2 to the point at coordinates 2, 1 to the point at coordinates 3, 2. You can see what happens here is precisely that. The first point is at position 1, 2, the second is at 2, 1 and the last one is at 3, 2. If we want to plot a graph of a function y equals f of x, we could do that by generating lots of xy pairs on that curve and then supplying them to Plt.plot. Let's do that in the next cell. We're going to plot a graph of the function y equals sine x, which we'll do using the NumPy linspace command to generate the x coordinates and math.sine as the function we're plotting. So we'll begin by creating these x coordinates. X's is going to be a NumPy array containing the x coordinates of the points on our graph. So we'll use NumPy linspace starting at 0 and ending at 2pi, so 2 star math.pi, and we'll take just a small number of points to begin with to see what it looks like. I now need to create the y coordinates corresponding to my x coordinates. We'll call the list of y coordinates y's, and we'll do this with a list comprehension. So it'll be math.sine of x for x in x's. Having done this, we've got our x coordinates and y coordinates, and we're ready to plot them. That's all we need to do this simple graph. You can see here, because I've got so few x's, I don't get a very good approximation at all to the graph of y equals sine x. Instead, I just get some very pointy straight line. But if we increase the number of points, let's say we change np.linspace so that its final argument is 50, and I have 50 equally spaced points between 0 and 2pi. In this case, we get a nice smooth approximation. The Plt.plot command can take many different arguments. In particular, you can add a title to your graph, you can label the x and y axes, and instead of drawing just a straight blue line like I have here, you can have many other styles of line. What the next cell does is to produce a graph or a plot using Plt.plot, which instead of drawing straight lines between the sets of coordinates you supply it with, just draws a red circle at each of those points. That's what RO does. R is for red, and 0 produces a circle instead of drawing straight lines. The next three commands set the title of the plot, a label for the y-axis, and a label for the x-axis. So when I run this, you can see here I've got red circles at the points whose coordinates I specified in the call to Plt.plot, and I've also got a label for the y-axis, for the x-axis, and an overall title for the graph. You can also have several plots on the same grid if you want. In the next code cell, I've defined some x coordinates, then a list of y coordinates for points on the graph of y equals sine x, and a list of y coordinates for points on the graph y equals cos x. I've called the y coordinates for sin x y's and the y coordinates for cos x z's. On lines 4 and 5 we plot those graphs, but we use different options to make the plots look different. The graph of sin x will be red plus signs, and the graph of cos x will be a dotted green line. There are many different options for here. If you want to see how they all work, you should follow the links to the documentation I gave at the top of this notebook. You can see I also supplied a label to these plot commands. That's because later on we're going to produce what's called a legend, which will tell us which line is which. I've set a title, an X label and a Y label, and this legend command will put a box somewhere on the plot, which will use the label defined in the plot commands to say which line was which. Finally, we can also have a grid on the plot. When I run this, you can see we get this horrible looking graph, but at least it does distinguish between the two different lines which we've plotted. The legend is this box at the bottom here, which tells you that the red pluses come from the plot command for which we supplied the label sin, and the green dots come from the plot command for which we supplied the label cos. The grey grid lines are there because of the last line which asked for plt.grid. Now there's something a bit weird about this, because there is a style of function call here which we've not seen before. So far we haven't seen a function call in which there is a named argument, like the calls on line 4 and 5 where we specify label equals quotes sine quotes and label equals quotes cosine and quotes. So let's look at this topic, which is called optional or default arguments to a function. The reason to introduce these is this. A function like plt.plot has many different arguments. There are all kinds of customizations you can do to plt.plot. Plt.plot wouldn't be a useful function if you had to specify a value for every single one of those different arguments. Each plt.plot call would involve specifying dozens of different arguments, which would make it extremely inconvenient for us to use. Python lets us get around this by having functions which take lots of arguments, some of which have a default argument which you don't have to specify. For example, as you've seen in a plt.plot command, if you don't specify what you want the line to look like, plt.plot makes the sensible assumption that you want a nice blue coloured line, drawing straight lines between each of the coordinates that you specify. You can override this by supplying an extra argument to plt.plot, like the one which we did when we wanted red plus signs for our sine graph. Let's see how to create our own functions with default arguments. So going back to a function definition here, I've created a function called f which has 4 inputs, but 3 of them have a specified default value. The way we define this is by having def f, and then an input which has no default, x, and then 3 more inputs, a, b, and c, which have the default values of 1, 2, and 3. Apart from that, the function definition is exactly the same as normal. You can then see that the return value of this function is a certain number depending on a, b, and c. Because a, b, and c have default values, you don't have to specify them in a call to f. If you call f of 0 with no value for a, b, and c specified, it will use the default values. So what it will work out is 1, the default value for a, times whatever the input x was, plus the default value for b, which was 2, divided by the default value for c, which is 3. That's 2/3. On the other hand, you can now override any of the defaults that you want. For example, let's say you want to stick with the default values for a and b, but you want to change the default value from c. So you want a value for c equal to 1. In this case, a and b will be the same as they were before, so we'll work out 1 times x plus 2, but this time we've specified a new value for c, so we'll be dividing by 1. You can see we really do get the answer I wrote in that comment there of 1 times 0 plus 2, all divided by the overridden value c, which is 1. If you want to change a, you can do that with the same syntax. by telling it you want to override A. Finally, there's no requirement to specify the non-default values in the same order that they were defined in the function f. If you want to work with b equals 10 and a equals 2, you can do that in any order you like, as long as you say that b is going to be 10 and a is equal to 2. So here this call will substitute 10 for b, not a, and will substitute 2 for a, not b, even though b and a in this function call were specified in a different order to how they were specified in the function definition. As you can see, the output here really was obtained by setting b to 10 and a to 2. The final type of plot I want to look at from matplotlib.pyplot is Plt.hist. Hist produces what's called a histogram or a bar chart. Here's how a bar chart or a histogram works. If you've got some numerical data and a collection of intervals, those intervals are usually called bins, what one of these plots does is plot a rectangle above that bin whose height is how many of the data points lie in that particular bin. To produce these in Plt, what you do is use the function Plt.hist. The first argument to Plt.hist should be the data that you want to plot, and the second argument should be some kind of specification of how the bins are going to work. You can either ask it just to use a certain number of equal width bins, in which case it will decide those in some algorithmic way using the data that you supplied it, or alternatively, if you want to specify the bins, you can supply a list. So you can use bins equal and then a list. If your list is b1, b2 up to bn, then the bins, so the intervals on the x-axis over which your rectangles are going to sit, will be the interval which is closed at b1 and open at b2. So I mean the numbers which are greater than or equal to b1 and strictly less than b2. And the next one will be the interval which is closed at b2 and open at b3, and so on, up to the final one, which will be closed at both ends. So let's try this. We're going to generate some random rolls of a dice. To do this, we'll import the random module, then define faces to represent the faces on our dice. So it'll be a normal standard 6-sided die with faces 1, 2, 3, 4, 5, 6. We'll then use random.choices. We didn't meet random.choices yet. What it does is sample k elements from a list with replacement. Again, this is a function with a default argument which can be overridden. If you want to sample k elements, you have to specify k equals and then how many elements you want to sample. Here we're going to roll the dice 1,000 times, so we'll specify k equals 1,000. When I've done this, rolls is now a list representing 1,000 different independent rolls from a die with 6 sides, 1, 2, 3, 4, 5, 6. We're now going to draw a histogram of those. The bins in my histogram are going to have endpoints 1/2, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5. The reason I've chosen that is that so all the 1s lie in the first bin between 1/2 and 1.5, and all the 2s lie in the second bin between 1.5 and 2.5, and so on. So this is a sensible choice of bins for this data. Before I start, you should test your statistical intuition. How flat is this going to look? So we expect that we get roughly equal amounts of 1s, 2s, 3s, 4 and 5s and 6 when we roll a lot of die, but how many die do I have to roll? Is this going to be big enough for it to look fairly flat? Let's have a go. So you can see, if I scroll down a bit, this is reasonably flat but not too flat. If we go down to 100 and rerun this, we get something which is not very flat at all, but if we go up to 10,000, then it really does look quite flat.